Okay, just to what I will go today, I will wrap up the introduction. I thought the introduction would take half the first lecture, but no. It actually took more than one lecture because I'm finished today. And then I will start introducing the multipolar expansion in GR. And I will demonstrate that it's a V expansion. Then actually is the I will have to tell you about the separation of the degrees of the counting of the degrees of freedom. How we do the counting of the degrees of freedom in general relativity, and I will do it in two different ways, one more formal and one more artisanal. So and then a little bit about green functions. Green functions, and I hope to get to the energy of gravitational waves. So basically, most of what I will do today will be at the level of the equation of motion. But then, starting probably from the end of today or from tomorrow, then we'll be working just at the level of the action and of the path integral. But first, we introduce things at the level of the equation of motion, and then we move to the path integral. So to wrap up the introduction, so I don't know if you saw my notes, but if you just happen to find my webpage, so basically you go to the website of this institute, not ICTP-SAIFR, but IFT, and then you look for me, and then I have a web page with many subpages. The subpage is teaching, contains these notes. For instance, this is a this is a plot of what I mentioned yesterday in the exercise session of the discrepancy between a linear distribution of time of passages of the binary pulsar. You remember, there was a pulsar in a binary system. It happens to be in a binary system with another neutron star, but only one of the two is a pulsar. I mean, probably also the other is a pulsar, but it's just not pointing to us. So one is pointing to us, so we see every passages, and these passages should be linearly spaced in time. But if you subtract the linear spacing, you get a parabola. That means that it doesn't go linearly in time, but there is a small piece that is quadratic in time. And this quadratic piece in time is exactly proportional to p dot. Basically from the convexity or concavity, I mean from the opening of the parabola, you measure p dot. So you see, these were the measure. So immediately when people realized this pulsar, that this pulsar was in a binary system, they like, oh, this is gonna be great. We're gonna do a lot of measuring general relativity. But of course, they wouldn't know how the points would evolve. But then they will neatly to a parabola, and then you see in 94, there was the Nobel Prize, so they stopped taking data for a while. They were probably busy giving talks and conferences everywhere, but you know, it's definitely a parabola. This is a 10 to minus 3 detection of the decay of the orbital period. So this is the main observable that proved, without any doubt, the observation of gravitational waves, and then we came to much more recent. This is the updated list of events of LIGO Virgo. You see, in y-axis is the mass, and in the x-axis, I think it's just, yeah, I think in the x-axis is, I don't know if these are in any order, in chronological order or not, but you see, there is few events that are compatible with neutron stars, so they are below 2 solar masses. Then all of the other are from 5 solar masses above, and those are the black holes. All of them are extragalactic. And you see there are few things we don't quite understand. For instance, you see there is an event which is not orange, not blue, that is 2.6 solar masses. That's a problem astrophysically to see, because it's too heavy to be a neutron star. We don't really know an equation of state for nuclear matter that would sustain such a heavy neutron star. And on the other hand, we don't have an astrophysical mechanism for a collapse of a star to give it such a light black hole. Basically, if the star is too light in the collapse of the star just explodes away. I mean, I'm just telling you, of course, this is not a demonstration. There are a lot of astrophysics going to it, but just to tell you that 2.6 compact object is a problem. Of course, it wouldn't be a problem if it would be the result of a merger, because if it's a merger of a neutron star, it can very naturally happen to have 2.6 solar masses, but then it's not the result of a collapse of a star. But then to have the result of a merger which is recycled in another merger, that's highly, highly unlikely. So however you put it, it's astrophysically a problem. Then you might have heard of, so then otherwise the gap between 2 and 5 solar masses in compact objects is kind of respected. And then people, you might have heard about a higher mass gap between 6 and 80 solar masses. The arrow means that the merger produces the final object. So you see the Y scale is nonlinear, so the sum of the two masses produced. So every event is 3 compact objects, no? 2 before the merger and 1 after the merger. So this is what we see, but you may wonder, oh, okay, but what we see is that funny shape, with increasing amplitude and increasing frequency. How do we translate from that shape to the masses that are so nicely plotted here? Well, and now let me sketch you this as a wrap-up of the intro, and then we go to more quantitative stuff. So basically, what happens is that, as I sketched yesterday, we have to take a correlation between the signal that is hidden in the data and our theoretical prediction. And basically, what is important for the theoretical prediction, I can probably stop sharing now. What is the share? The share. Where am I sharing? I don't see the Zoom window here. Is this computer which is sharing? Okay, anyway. I'm sorry, I'm not supposed to share anything more. So let's focus back on the blackboard. So the phase of the gravitational wave is the angular velocity of the orbital system integrating over dt. I mean, there's not much information. Okay, there is a 2 actually, because the orbital velocity when the two objects swap position, it's already a cycle from the gravitational wave, but it's half a cycle for the orbit. So there is the 2, but I mean, we're not interested in the 2 now. We are just interested in the relationship between the phase of the gravitational wave and the orbital dynamics. I mean, this equation, apart from the 2, is really trivial, no? I'm saying that phi dot is equal to omega. I mean, that's not a lot of physics. So let me massage this to introduce a little bit of physics. I multiply and divide by gm. Okay, and still this is quite trivial. But then you remember, this was V cube, okay? Yesterday we used it many times in the Kepler's relationship. And then we do the following. Well, we don't really know how the omega evolves with time until we plug in the dynamics, no? That's actually the rest of the course is about how we make the bridge between the fundamental gravity and the dynamics of the system, and the dynamics of the system will allow us to compute the phase, and computing the phase and its correct behavior will allow us to take a cross correlation with the data and extract the information about the masses, for instance. So look at this. Now we do this trick. Okay, I'm just playing with the differentials, and this is again pretty trivial. So dE simplify, dV simplify. Sorry, dt and dV. Sorry. It's dV. What did I do wrong? Yes, I have to put. Yes, now it's correct. I have the original dt is here, then dE simplify, dV, and dV simplifies. But you see, now you recognize the functions that belongs to the dynamics. Here I have dE in dV, that basically, if I have my relationship between the energy and the velocity, then I have it. Then this is the luminosity function, E dot, and then I have to integrate it in dV. And so in this way, I have my phasing as a function of V. V is monotonically increasing, so it's a good parameter to label the different phases of the orbit. And so look at this. So if I go back to my Newtonian formula, I should have -1/2 mu. Let's write it as eta, m v square, and then we will have all sort of post-Newtonian correction that we'll learn how to compute starting from 10 minutes from now. And then this is the flux function, the luminosity function. Then we have 32/5. The 32 I haven't demonstrated, but it comes out of the computation. And then I have all sort of correction. And this is dV, okay? So now look carefully at the leading order. The leading order is given by the Newtonian energy divided by the leading order flux, which again, I just throw in, I haven't demonstrated. A V cube in front, yes, thank you. There is a V cube here. The flux, I mean, if you consider that this is the energy of the system, then E dot is negative. So the plus and plus in phi, there is a V cube. D in dV, it was a V square, so when I derive, I get V, and the 2 goes away. So overall, I have a V4 in the numerator and a V10 in the denominator. So overall, this, the M and M simplifies. Sorry, this was over G. G simplifies. So apart from numerical factor, this gives 1 over V to the 6, and then corrections. So this function here, the energy of circular orbit, is natural to have only even power of V's, no? Because it shouldn't change if I change the arrow of time. The flux, no, it can have odd power of V, and indeed it has. It just doesn't. It just happens not to have V to the 1 because of the structure of the GR. We'll see, but it has all odd power of V's. So basically, we get to this formula for the prediction of the phase. Now, the crucial observation is that we need the phase to be right to less than 1 radians, no? Because we want to correlate something which is oscillating with our model for the same thing. And if you want to take a correlation, we cannot say correlate the cosinus of the phase which is varying with the cosinus of what we think to be the same phase, but dislocated by 1 radians, no? This dislocation must be less than 1 radians. Here you have a few simplifications, so at the end, you get just 1 power of the symmetric mass ratio. We have some number. You have no dimensionful quantities. No, the mass must go away because the phase is dimensionless, V is dimensionless. So since V is smaller than 1, when you integrate, this goes as 1 over V to the 5. So it's clear that unless you get also the V to the 6 term here right, you can never even hope to get less than 1 radians error, okay? Because here, the term you are neglecting, suppose I stop the V to the 3, I'm neglecting a V to the 4, that once I integrate, it becomes a 1 over V. 1 over V is large, because V is smaller than 1. So that means that if I want to get the phase right to correlate with the data, I'd better to predict high terms in my perturbative expansion. Otherwise, my correlation will be very poor, and the masses that I estimated, that I showed you earlier, will come out, I mean, very biased, okay? So this is a mixed blessing. On one side, I need a lot of information about the highly self-interactive, non-trivial part of gravity to predict the phase right. On the other hand, I know that my experimental results are sensitive to high-order interaction of gravity, like no other observation before. So I have a window, I have a clue to understand the high-order self-interaction of gravity that that was never available before, specifically to this system of compact black holes at few tens of kilometers away. Question?
Sorry, I was about to ask, like, how did you get from the EDV to that expression on the right?
So remember, the energy is -1/2 symmetric mass ratio mass V square, and then I will show that there will be general relativistic correction.
All right. Okay.
But this is just the Newtonian.
The Newtonian. Okay.
This you cannot dispute.
Yes. Sure. Okay.
But this we'll see. Okay. So D in dV then it becomes linear in V because I derive. Yeah. And this is the quadruple formula that I just throw in. I haven't demonstrated yet, but you can understand that if I start with some formula, then I will have post-Newtonian correction. A question here. Yeah, the question is about the even power of the correction to the energy. So this is the energy of circular orbit. So how, I told you that if you are in a circular orbit, you have only one parameter, the period or the velocity or the radius, they are all interdependent. So I take the velocity. So the energy, it shouldn't change if if I move one side or the other side. Basically, if I do a time reversal, or it cannot change, just because it's the energy of circular orbit. This is not true for the flux, no? Because the flux is intrinsically time asymmetric, because it's d in dt. But the energy should be time symmetric. So here I have only even power. Here I have all odd and even power, with the exception that v to the 1 is not present. It just happens because of the structure of general relativity. For instance, if you have some other funny theory, you might have v to the 1. So for instance, seeing an effect v to the 1 with respect to the v to the 10 leading order would be a smoking gun of a non-GR. But I will show you, we'll demonstrate there is no v to the 1. Actually, so here the surprise is not the presence of the v cube or v5 or v7, but the surprise is the non-presence of v to the 1. Okay, so let's start with some nice and quantitative formulae now. So, yes. So, as I told you today, I deal mostly with the GR at the level of the equation of motion. But you are amplitude people, you are, so I guess you're not scared by the path integral. Use path integral on daily basis. So, starting from the end of today or tomorrow, we'll be using path integral all the time. Because I have to, sometimes I give this lecture for cosmology, sometimes I give this lecture for particle physicists, and of course I have to rescope quite heavily. But I guess you're not scared by the path integral. But anyway, since you're not scared by the path integral, you should be able to see things. Probably you haven't seen, you're not used to see things at the level of the equation of motion. So let's do it now. So at the level of the equation of motion, we must deal with the Einstein equation. So I do this as a start because, if I want to work at the level of the action with the same level of accuracy, I need quadratic pieces. Okay, it's not a big deal, but if you write quadratic pieces for the metric perturbation, become a bit ugly. Not too ugly, but it would hide the physics a little bit. So let's not hide the physics to start with, and then we go to fully fledged Lagrangian. So this is the Einstein tensor, and this is the energy momentum tensor. So there is a conservation equation. The gradient of this is, the divergence of this is 0, and the divergence of this is 0. This is a consistency, and this consistency. And then we linearize around Minkowski space, as I mentioned yesterday. So we'll deal only with this, will be our dynamical degree of freedom. So the Einstein tensor is made of the Riemann. The Riemann is one derivative of the Christoffel. And so the Christoffel has one derivative of the metric, so second order differential equation. So it just happened. Let me skip. Nowadays, when I was your age, I had to derive this by hand, which is not a big deal at linear order, by the way. But nowadays, there are a lot of software in Mathematica that do the expansion for you. It's not too difficult. And then we get the expansion of the left-hand side is, let's see if I remember well. Now I shoot it and then I check the notes. D rho h bar rho sigma minus d nu. D nu d rho h bar rho mu. Let's see if my shoot was correct. I got it right, yes. You see? I've been teaching GR for too long, so that's why the director of my institute asked me to teach electrodynamics next semester. So now I cannot recycle this anymore in the next course. Okay, so it's not, you could think of more structure than this, no? If you just think of two derivatives acting on a rank 2 tensor, there are more structure than this coming out. But it just happened there this. And I haven't defined H bar. H bar is just the trace reverse, how it is called H. This is the definition, and H is just the trace. So, and then in a second, I will split space and time. And then when I split space and time, you have to remember that I use the metric minus plus plus plus. This is probably different from all what particle physics do, but this is what GR people do. So scientifically, I was born in particle physics, but then I moved into GR, and so I'm a hybrid, but I decided to pick this metric. So, okay, so it's linear, so it's not a big deal. What's the ugly thing about this? The ugly thing about this is that mixes all polarizations, okay? So it's linear, but I mean, if you want to know one polarization, it's not trivial. And there is one thing which is even uglier, that I cannot solve for all of the polarization. And that you don't see, you don't see by eye probably, but you can check it, that the general relativistic coordinate transformation the x prime mu, the x prime nu. You see, this is the if I make a coordinate transformation, x prime mu going, sorry, x mu going to x prime mu equal to x mu plus xi mu. This in general relativity, I can do this. You know, gauge theory, you know, it was inspired by this. And then at a linearized level, this implies that h bar, let's say h mu nu must go to h prime mu nu equal to h mu nu plus, actually minus with this definition, minus nu minus x nu. Okay? This is the transformation of h, and the transformation of h bar, it's trivially derived by this. Let me write just the transformation. There will be minus xi mu nu minus xi nu mu plus xi mu, xi half, the divergence on eta mu nu, without the 1/2. Hopefully. Yes, without the 1/2. Okay. So this is a gauge transformation. This is a coordinate transformation in general relativity. That and so h or h bar inherits this for a linearized transformation. And so you can check that if you apply this transformation to this left-hand side, the left-hand side stays invariant. So in principle, no, basically, if you think of it in terms of the Lagrangian, that means that this linear equation must come from some h mu nu h rho sigma times a second-order differential operator. So the Lagrangian must be of this type, where this the second-order differential operator has a kernel which is non-zero, that basically kills whatever is of the type of xi rho sigma psi plus xi sigma rho. So I use the column as a gradient, okay? The column just means derivatives. So you can check that if you do this transformation, this stays invariant, and this is inherited from the Lagrangian that has a quadratic piece that takes, there is a quadratic operator that combines two h's that kills an object of this form. I mean, this is nothing new. In electromagnetics, it happens all the time, no? You have in electromagnetics, you have f squared, and you know that f squared is exactly 0 if the gauge field is a pure gradient. This is basically a generalization of a pure gradient when you have one index bar. Okay, but this is normal. I mean, when you have a gauge theory, you're not supposed to have the dynamics for all of the degrees of freedom. Your theory is supposed to give you dynamics only for the physical degrees of freedom. And here there are hidden 4 gauge degrees of freedom. The point is that here they're hidden very well. It might be difficult to disentangle them. So we impose a gauge condition that we can always do by suitably choosing 4 function xi mu's, and our gauge condition will be this. Basically, the divergence of h bar is 0, not of h, the divergence of h bar. In this case, under the gauge condition, we kill all of these. And so we get to a nice linear equation which that decouples all polarization. So now every polarization is on its own. So now it's trivial to solve this. The solution to this is h mu nu, the minus 1/2, I bring it to the other side, 16 pi g t mu nu divided by box. Okay, I put the box on the other side, I'm fine. Okay. You accept, no, come on, you accept this. No, I go to Fourier space, this is just k squared, and I put it there. If you don't want to go to Fourier space, then this is understood that this is minus 16 pi g integral of t mu nu t prime x prime convolved with t minus t prime x minus x prime divided, yeah, that's it, dt prime d3 x prime. Okay? And this is the green function. The green function that we want to use is not the Feynman green function, but is this. Okay? So you can check that it has the right dimensions, and is the standard green function that you must have used if you studied on Jackson. No? If you study classical electrodynamics, this is the standard retarded green function. So all of these might be very, very far from what you know from particle physics, no? Because in particle physics, in electromagnetism, what you do, you add the gauge fixing term to the Lagrangian, then you make the kinetic term of your Lagrangian invertible, and then you invert it, and then you write this as 1 over k squared minus omega squared. But this is exactly equivalent. This is exactly what I'm doing, just in direct space and not in Fourier space. I will demonstrate in a second. What is important is that here I'm using the retarded green function. I won't be using the Feynman green function. What for? I mean, it's astrophysics. I mean, the field at some distance must depend on the path of the source. The Feynman green function, we'll see, is acausal. Okay, this is causal green function. The Feynman green function will mix past and future. But this is what you want in particle physics, no? Because in particle physics, you want some state you prepare to come in at minus infinity, and some specific state you observe at plus infinity, because your detector cannot detect anything. No, it doesn't detect neutrino most of the time. For sure, it doesn't detect dark matter. So it only detects photons, say, at some specific point. So you want scattering amplitude that have some prescribed initial condition for some experimentally prepared state, and some prescribed final state, which are the ones that your experiment can detect. Okay, so this will be very, very different from G Feynman. Okay, so let's elaborate a little bit on this. Yes, question. Yes, very good. Okay, yes, you're right. I should do this first. Okay, this H mu nu is a symmetrical to tensor, so it has 10 degrees of freedom. So you say, oh, okay, look at this. Then I have 10 waves. Then I have 10 polarization that behave like a wave. Let me rewrite it in this way. No? This is a box equation. This is a wave equation. And then I apply the box to this. I see the temporal, this is a linear equation. I have 10 radiative equation. Of course, I haven't added non-linearities, but non-linearities just change quantitatively the field. They cannot kill and allow in or rule out new degrees of freedom. So you would be mistakenly led to say that the gravitational field has 10 relative degrees of freedom. This is badly wrong if you say that you won't pass my GR course. Okay? Why? First, because I have 4 gauge conditions. So at most, these are 6. But then you say, okay, fine. These are 6 relative degrees of freedom. Wrong again, very wrong. Okay? By the way, this took 40 years for the scientific community to understand that here there are only 2 radiative degrees of freedom, and not 10 and not 6. Actually, Weil, beside Einstein, Weil was probably the first, beside Einstein, to understand that. And he mocked the people who didn't by saying, well, there are 2 degrees of freedom that propagate with the speed of light, which are relative, and there are furthermore which propagate with the speed of thought. Instead that you can let them propagate with whatever thought, pensamento. Because they say, okay, you can let them propagate with whatever speed you want. Let's see how this comes. But basically, if you want a formal derivation of this statement, that you have only 2 relative degrees of freedom, 4 longitudinal degrees of freedom, and 4 gauge. Okay, first, most of you probably don't even know what is 4 longitudinal degrees of freedom. 4 gauge, yes, you understand. I mean, I have 4 gauge transformation, 4 coordinate transformation. They soak up these 4 degrees of freedom. That there are 2 relative degrees of freedom. Maybe you never demonstrated in your life, but you heard it all the time. The graviton has 2 polarization. The photon has 2 polarization. Why on Earth it has 2 longitudinal degrees of freedom, and what does it mean? To explain what it means, let's do the simplified exercise of electromagnetism. In electromagnetism, you have a similar decomposition of the degrees of freedom, but the A mu has only 4 degrees of freedom. They happen to be 1 radiative, 1 longitudinal, and 1 gauge. Sorry, 2 radiative, of course. 2 radiative, 1 longitudinal, and 1 gauge. So let's do in electromagnetism, and then the same construction that I will do right now applies to gravity. Of course, you have to change a little bit, because in gravity you have one more index. But the construction that I'm going to do now, I won't do in gravity because it takes 1 hour and a half. Then we soak up 1/3 of my lecture time. But you find it in the notes, and the notes are just a cut and paste of a paper from the 90s. So it's nothing fancy, nothing exotic. So for the moment, let's go to electromagnetism. I know here there might be a coefficient, but I mean, we are just counting degrees of freedom. We don't care about coefficient when we count degrees of freedom. And let's split this equation into 2. Into the time part and the space part. The time part will be d0 f0i, of course, the time part will be this. Of course, I cannot have d0 f00 because f00 is 0. But then I have d0 f0i, this will be d0 di a0 minus d0 ai. And this is equal to rho. And now I want to do a crucial step. This is very crucial. Stay with me now, because it's very crucial. I say that I decompose my 4 components gauge field into A0 stays as it is, and then the space part I decompose as a transverse part that satisfies divergence of A bar equal to 0. So these are 2 degrees of freedom. It has an index, so it has 3 entries, but it's only 2 degrees of freedom because it has 1 constraint. And the third degrees of freedom, I throw it into longitudinal part. So is this decomposition unique? Yes. If I take the divergence here, this is 0. Then I take the Laplacian of A is equal to the divergence of the initial, and then the Laplacian can be inverted with the same trick of the box. I just bring the Laplacian in the denominator, and fine. I just use the green function of the Laplacian, which is similar to this. It just doesn't have the retarded piece. Okay. And so I plug this into here, and then I get Laplacian of A0 minus, actually plus, because I use metric minus plus plus plus. This is a contravariant derivative, is minus time derivative, a dot, because this will be di ai. I have to pick this piece, and this is equal to rho. Okay? So I got this decomposition of my gauge field, which, by the way, is called scalar vector decomposition of my gauge field. So this is a scalar that becomes a longitudinal vector, and this is a real transverse vector. Then I take the space part of this, and the space part of this will be d0 f0i plus dk fki. That will be equal to d0 ai minus di a0 plus dk ai minus ai minus dk ai. Okay, and now we apply the decomposition. So when we apply the decomposition, I put on one piece everything which is transverse, and another piece whatever is not transverse. So let's look at the transverse piece. The transverse piece will be minus a bar I double dot from here. So here I get the A0 goes into the scalar part. Here I have plus Laplacian of a bar I. And here, if I put the a bar piece of this is 0. Because, sorry, this is d-i-a-k. The a bar piece, this is 0 because you see there is the k, ak, it kills the transfer part. So you see, for the transfer part, I got everything. So now let's take the longitudinal part. So the longitudinal part will have a di minus a double dot, okay? Because this will be the gradient of the small a. with two derivatives, one with the plus, one with the minus, is minus a double dot. And here I took everything, both the longitudinal, both the transverse. Here I only the scalar part, and the scalar part is the dA, which is already out, and then I have minus a0 dot. And then I have, from this part, here I already took this, the transverse part. I need to take the longitudinal part. This is the Laplacian of the gradient of AI. The gradient is already here. And here I have again Laplacian of the gradient of AI. So this simplifies. Okay. Clearly for the longitudinal vector, this is 0, no? So look at this. And this is equal, and then I have to do the same decomposition on the sources as well. Then I say that my source is a transverse source plus a gradient of a scalar. So now I split the equations, and look at this, what I get. I get this, let me skip these intermediate passages, which I have now. So I get from here the A0 plus A double dot equal to minus J with the DI applying to both sides. No? I took this part. And then the other equation I have is box A bar I equal to J bar I. So look at what I found. I found that the transverse part is a honest radiative degrees of freedom. It's not gauge, I mean, it's purely radiative, no? Because it does satisfy a box equation. Okay? So there are 2 degrees of freedom that definitely are radiation. Then look at this. There is 1 degree of freedom that is not radiation. It satisfies a Laplacian equation. When it satisfies the Laplacian equation, basically that its dynamics is fixed by the source. By the way, this is gauge invariant, because the gauge transformation of A is so in particular, A0 goes into A0 minus lambda dot. This is a minus lambda dot. A bar I goes into A bar I. It doesn't change, because this only changes the longitudinal part, and A goes into A plus lambda. This is the action of a gauge transformation over small a, I bar, or A0. And then you see A0 plus A dot. Sorry, here was a dot missing. A0 plus the dot is gauge invariant and satisfies Laplacian equation, a Laplace equation. So it has to follow the source. It's not a radiative degrees of freedom. It's a longitudinal mode. I mean, this shouldn't surprise you, no? Electromagnetism, let's forget about gravity. Electromagnetism is responsible for radiation, light, which is so common, and it is responsible for Coulomb attraction and repulsion. This is Coulomb attraction and repulsion, and this is radiation. Okay? So there is one thing which is electrostatic, electromagnetic forces that are mediated between charges and currents, and one thing is radiation. And you see, the two are qualitatively different. One satisfies a box equation, one satisfies a Laplace equation. But then what is? Look, we have this very same combination, except that it has an extra derivative, that satisfies a different equation. So either these two equations are the same, or the only solution to two different equations for the same quantity is 0. Let's see if we can avoid this being 0. And basically, we take the divergence here, we take a time derivative here, we get that these two members become the same, Laplacian of A0 dot plus A double dot, Laplacian of A0 dot plus double dot, but the right-hand side become R dot, so when I subtract the two members, must be equal to Laplacian of J. Is it true that rho dot is equal to minus Laplacian of J? Or if you like, that this is the equation of continuity, no? Because the divergence of the initial current that we just traded for the gradient of a scalar. So yes, these two equations are the same, provided that the current is conserved. So electromagnetism wouldn't be consistent unless the current is conserved. But when the current is conserved, that's fine. The two longitudinal equations happen to be the same. And so they both say that there is a gauge invariant combination of the longitudinal fields that satisfies the Poisson equation. So this is the longitudinal field that mediates Coulombic interaction and so on. And this is the radiative field that propagate light, radio waves, whatever. Okay? So we have demonstrated this separation. 2 radiative degrees of freedom, 1 longitudinal, and 1 gauge. Okay? So in electromagnetism, it shouldn't be difficult to accept it, no? Because from the very beginning, even at high school, no? You rub a piece of wool, and then you get electrostatic forces. That's A0 plus A dot. Okay? And then light, I mean, since we are all accustomed to light, I mean, you cannot deny the presence of this radiation field. So in gravity, this scalar vector decomposition takes a slightly different name, scalar vector tensor decomposition, because we have 1 index more. And so we have to decompose things with 0 index, with 1 index, and 2 indices, and it comes out this separation in degrees of freedom that I sketched, yes. And what comes out is this. We have 2 radiative and 4 gauge and 4 longitudinal. This is the non-trivial part, because Newtonianly you would expect 1 longitudinal degrees of freedom, the one that mediates gravitational attraction. After all, we all feel the attraction of the Earth, and etc. But in general relativity, there are 3 more of longitudinal degrees of freedom. So if you ever study cosmology, this SVT decomposition is done in detail to treat cosmological perturbation, and it's even more difficult than in Minkowski because it's expanded over a Freeman-Robertson-Walker background. But in any book of cosmology, the SVT decomposition is done. So you apply this SVT composition in Minkowski, which is a little bit simpler than in cosmology, and you get this separation. Of course, this is just separation of degrees of freedom. It doesn't matter which is the background you work on, which is the interaction. It's just now counting on degrees of freedom. Okay. Then, of course, the specific interaction will change on the background, and will change on which background you put your theory on. But this separation stays the same. So I don't do now on the blackboard this the generalization of the SV. I don't do the SVT decomposition applied to gravity. I just state the result, hoping that you can digest it on the basis of the gauge field example. If you cannot digest it, actually, anyway, you should go to the notes and read the 5-6 pages where this is derived in all mathematical details. Okay? Any question on this? Yes?
The little way there that you defined, I didn't really get where that come from. Like,
so the little is just a definition. So I say that my space part of the gauge field is a transfer vector. So it's a vector. It has 3 space indices, but actually it has 2 independent components because it satisfies a constraint. And then I define the rest. Basically, I say that I can cancel this now. I just say that my whatever is the difference between the total of the space part of the gauge field and its transverse part, I define it as a gradient of a scalar. And how do I find the gradient of a scalar? Well, I apply another divergence, and then it gives me Laplacian of A equal to the divergence of A, because this, by definition, is 0. And then I solve A is equal to the AI divided by the Laplacian, which by this I just mean the green function of the Laplacian that, you know. Okay, there is one tricky point, is that this decomposition is non-local. To know A, small a, in any point, I need to know capital A, the original A, in all of the points, no? Because this green function involves an integral over all points. But it's non-local in the direct space, it's local in K space. So, I mean, in one of the two, it has to be non-local. But just be careful. I mean, you cannot measure this little a by making a local experiment. No, it's not physical. But at the end of the day, this A is just related to the potential. Whenever you write the electric field and the B field, the magnetic field, which are physical, which you can measure with local experiments, it will only appear derivatives of this A, derivatives of A0, and at the end, you will always appear local combination of small a and A0 and so on. So this is the composition. Again, let me stress it one more. It's non-local in the sense that small a is non-local with respect to the original field, and then by consequence, the A bar must be non-local with respect to the initial field. But it separates nicely the degrees of freedom. And it's local in the K space. It's not local in that space, but it's local in K space. So, and then jump, we say that was the decomposition for the gauge field, And this is the composition of gravity. I haven't demonstrated, look at the notes, or just accept it. Question? Yeah, I will repeat otherwise. Yes, I mean, so in electromagnetism, no, you can kill the degrees of freedom by putting this constraint. I say, I want to work in this gauge, okay? If you work in this gauge and then you go back to the original equation, the original equation is d mu, a nu, d nu, a mu equal to j nu. So if I enforce this constraint, this object goes away, and then my equation of motion becomes box a nu equal to j nu. So if I work in this gauge, then I get 4 equations, 4 decoupled. I mean, electromagnetism is not self-interacting, so it would have been decoupled anyway. But you get 4 linear equations that mistakenly give you the idea that all 4 polarization are radiative. But it's a mistake, it's not true.
Now it's working. So on the Hamiltonian formalism of electromagnetism, the gauge symmetry is generated by a constraint, which is Gauss constraint, and then we have this argument.
Wait. No, you're mixing many things. Wait. So what you do in electromagnetism, you add by hand a dA squared to the Lagrangian.
Yes.
Okay.
Okay.
And then to impose these constraints, in order not to let propagate in internal states some unphysical degrees of freedom, you have to introduce the ghost. Sorry, the question goes well beyond the scope of this course, but just since it has been raised, I have to answer. Okay, so what you do in electromagnetism, you have a Lagrangian, which is F nu square, minus 1/4, and then you add by hand dA square. By adding by hand dA square, you do what I just canceled, that you make the equation much simpler, much nicer, but you are solving, in principle, you are solving for something different than electromagnetism, because you added by hand something that didn't belong. And then when you quantize things, for instance, when you have process, I mean, suppose you have two charges changing. Okay, in electromagnetism, this doesn't really happen, but you do the same for gluons. So suppose you have these kind of diagrams, and in order to avoid to let propagate here inside extra degrees of freedom, which do belong to this theory, but this theory is not the gauge theory you started with, then you have to add the propagation of ghost. Basically, here you have ghost, and here you have this A mu in this fake theory, because this is not gauge theory, spin 1 and gauge theory. This is gauge fixed spin 1 theory, which is not the theory you started from. So you screwed your theory to make the kinetic term invertible, but then you have to fix it, and then you introduce the ghost, because here in this theory there are extra degrees of freedom that were not originally in your theory, and then you introduce the ghost to eat them back. I find this mechanism, I mean, it works, but I don't find it very elegant, but I mean, that's my taste. I mean, okay? That's what you do in this ghosting. That was your question about?
This is good. Can I ask another question, which is also not specifically related to the course? But gravity also based on form of Gauss law, in the sense that the energy is...
So in gravity, so in principle, we do, at the level of the equation of motion, we do the same thing. No? When we cancel these terms, we did exactly the same thing. We imposed dH bar equal to 0. Which is very analog to dA equal to 0. But when we do that, then we'll see, hopefully, maybe not today, but one of the next things I will do is to recast this in a Lagrangian formalism. And in a Lagrangian formalism, what you do is basically the same what you do in electromagnetism. You add by hand a term which was not there in gravity. And added by term, the term was not there in gravity, you make the quadratic term invertible, and you're fine. But then you have to be careful, you're solving a different theory. In principle, if you let graviton do a loop, in this gauge fixed theory, which is not original gravity, you are allowing extra degrees of freedom to propagate. But this is a classical gravity course. All what I do is classical gravity, so this diagram will never be under my concern, because these are quantum, and what I'll do is classical gravity. So in classical gravity, in principle, you should never worry about the fact that gauge fixing in the Lagrangian, you are introducing extra degrees of freedom that screw your theory. Almost never, actually, almost never. In some times you have to check. But you don't have to worry about ghosts because ghosts don't couple to matter. Ghost only appears in loops, and loops by definition are quantum, and I don't do quantum physics. I'm a classical guy.
Thank you.
Okay, all what I do here, when I introduce H bar will be just for fun. I mean, H bar can go to infinity for me, absolutely, and nothing will change. Okay, so this was for the counting on the degrees of freedom. So now let's go back to the equation of motion, and I will show you a simplified derivation of the fact that gravity has 2 radiative degrees of freedom. A simplified derivation. Okay, I go. No questions, I do it now. So, my simplifying. Yes, electromagnetics now we dominate. We have no worry about electromagnetics. It's all carved into your mind, this separation of degrees of freedom. So, how many radiative degrees of freedom has the gauge field? The spin 1 gauge field, how many radiative degrees of freedom has? How many degrees of freedom has a spin 1 gauge field? How many radiative? 2, you see? You learn, okay. I don't need to insist on it anymore. Good. So, what happens here? I have my HP nu, my HP nu bar that satisfies this this coordinate transformation. Then look at what happens. If I want to preserve my gauge condition, can I shift my H bar by some psi and still satisfy my gauge condition? The answer is yes. This is preserved under gauge transformation, satisfying box xi mu equal to 0. You see? Because if I take this is the shift in H bar. If I take the divergence of this will give me, so the divergence with respect to mu, say, this will give me d mu, d nu x mu, minus box xi nu, minus d mu, d nu xi mu. So when I take a divergence of this will be equal to minus box xi nu. So you see, I can keep staying in my Lorentz gauge condition, and I keep doing, I mean, you thought you already used all of your gauge transformation by going to the Lorentz condition, no? I use 4 degrees, my 4 degrees of freedom to go to Lorentz condition. But now I tell you something more. I tell you that while I'm already inside my Lorentz gauge condition, while I thought I already used all of my gauge freedom with imposing the Lorentz gauge condition, I still have some freedom. I can make an arbitrary coordinate transformation, well, not really arbitrary. I can, provided a specific transformation that satisfies box C equal to 0, and I don't move out of the Lorentz condition. So I still keep this nice linear decoupled equation. So I can do it, and basically this C box, this extra degree of freedom of my coordinate transformation, will allow me to kill 4 more degrees of freedom. I just shift this, and basically I kill 4 degrees of freedom with my Lorentz condition. And then I kill I kill 4 more degrees of freedom by xi mu nu. Let me call all of these xi mu nu. This is a 2 tensor, which is just this. It's just the shift of delta H bar. I do a coordinate transformation. I can do and still be in the Lorentz condition because my extra coordinate transformation satisfies this. And look at this. Basically, I have an object that can kill 4 more degrees of freedom. Why? Because this satisfies the same equation as my field. So now can you make the bridge with what I told you earlier? Remember? In gravity, I had 2 radiative that satisfy the box equation. The box equation is some homogeneous solution and some solution that depends only on the source. For longitudinal physically they satisfy a Laplace equation. So they must follow the source. If the source goes away, they go away too. There's no homogeneous solution to this. That goes to 0 to infinity. And then I have 4 gauge. The 4 gauge degrees of freedom is the one I kill at the beginning with my the Lorentz condition. These 4 longitudinal degrees of freedom are the ones I'm killing now. I'm killing now by this extra coordinate transformation that keeps me in the Lorentz condition and is killing the longitudinal degrees of freedom. Why? Because I'm looking at degrees of freedom that satisfies a homogeneous equation, and longitudinal degrees of freedom don't satisfy a homogeneous equation. Okay? So this is the standard derivation that you find in GR books of the fact that gravity has 2 radiative degrees of freedom. You have 4 killed by the Lorentz condition and 4 killed by this extra condition. You can apply this extra condition in vacuum, and this extra condition in vacuum corresponds to killing the longitudinal degrees of freedom. And so you are left with the honestly, really 2 radiative ones. If you want, like in Maggiore's book, no, which is a kind of reference for gravitational wave introductory course, what do you get? You get that you have your H00, H0I, and then you have Hij. Okay? This is Hij. So what you do, you kill the 3 H0Is with the 3 of this condition. Then you take the Lorentz condition, one of the 3 Lorentz condition. Once you have already killed the 3 H0Is with 3 of this condition, this is already 0, then you get the H00, it's constant, but it cannot contribute to a wave if it's constant, no? So then you're killing H00. So you're killing H00 with the 1 of the Lorentz condition, and you're killing H0I with the 3 of my extra transformation. And so I'm left with the Hijs. Then in the Hijs, I kill the trace with my remaining box coordinate transformation. And so I'm left with the 3 Lorentz condition I haven't used. Is d mu j, which is d0 h0j plus dk hkj. These ones I already killed here, so I'm left with this. If I'm looking for specificity to a plane wave moving in z direction, this means the derivative with respect to z of hz, whatever other index, is 0. But again, if a wave does not depend on the z, it cannot depend on anything, no? Because this is supposed to be t minus z. Then if it cannot depend on z, because the gradient with respect to z is 0, then it means that I kill all of these components. So I kill all the z components. I kill 3, but then this is symmetric, so I kill 5. I kill the trace, so whatever survives is hxy, hyx, and then hxx, and then hyy is not independent because the trace is already constrained to be 0, so it's hxx. So actually, people don't call this xx, xy, and but call h plus, h cross minus h cross, h plus. Sorry, this is plus, of course, it's symmetric, this is minus. Okay? So these are the 2 surviving radiative polarization out of the 10 components of the gravitational field. In my gauge fixed, I mean, this is severely gauge fixed, okay? This is not generic. This is in one specific gauge, which is called the TT gauge. Transverse, traceless. Sorry, traceless, transverse, and this condition I use to kill the time component, so the time component, whatever is one index with time, I just forget it. And in the space-space part, I kill the transverse and the trace, so this is called transverse traceless. Yes, question? No, wait, okay, okay. Listen, I realize, so the question is, does H00 satisfy the Coulomb equation? Wait, not quite. Physically, yes, but you remember, in the Lorentz gauge, the equation is this. This is in the Lorentz gauge. So all polarizations in the Lorentz gauge satisfies the box equation, all polarization. But when you go to physics, if you want to take into account what is the physics of these degrees of freedom, A00 will be pure gauge or longitudinal. In the case, basically, if you go to the gauge of the Schwarzschild metric, H00 is the longitudinal degrees of freedom that mediate Newtonian attraction between black holes, because H00 is, you remember, it's 2 gm over r, no? For instance, in Schwarzschild. And that's correct. It's not zero, and it's physical. I mean, it's very physical. It's what keeps me on the ground, no? So you cannot say this is not physical, but this is certainly not radiative, okay? Yeah, for instance, they're related in Kerr space. You have the H0i's that are turned on and are proportional to the spin, for instance. In some, I mean, it depends on the gauge. Depends. So you can see them as related to the spin degrees of freedom that is sourcing the A0i. But again, they are longitudinal, they're not waves. But this is depend on the gauge. You can find other gauge where they are sourced by other things. But physically, you can think of A00 sourced by the mass, A0i sourced by the angular momentum. There was another question? Yes. No, this residual gauge invariance, the question was about this residual gauge invariance, is present in any background. Because this continuum degrees of freedom is really fundamental. It cannot change if you tweak a little bit your background. You're not changing. The number of degrees of freedom is discrete. You cannot jump from 2 to 3 to 2 to 1. So, if I put the if I put the sources to 0, these all longitudinal degrees of freedom dies just because they have to follow via Poisson the behavior of the source. And since they die, that's the right way to kill the non-radiative degrees of freedom and isolate the only radiative degrees of freedom. So this is the composition I can do on any background. The point is that when I do on different background, then the specific, basically, if I do in Freeman-Robinson-Walker, whatever, it only changes that box is the box of Freeman-Robinson-Walker, but the equation doesn't get any extra factor. If you do a more perverse space-time, then might get some, I don't know, curvature of the background appears here. But, okay. Did I answer your question? Okay. So, and then, so now that we have with this more artisanal way, so the SVT decomposition is the correct way to isolate the degrees of freedom, but I did it only for the gauge field. You can study. So this is the more artisanal way to use these extra degrees of freedom. But the first time I read it, I was a kid, and I said, oh, but this is strange. What does it mean that I already used the gauge degrees of freedom? What does it mean, this 4 extra? Well, it means exactly this, killing the longitudinal ones. Then there is an even simpler way to isolate the 2 radiative degrees of freedom. That is the following. Look at here. Once we know that the end of the construction is to isolate the space-space component, is to kill by hand the time space and time component, and isolate among the space-space components only the ones which are transferred to the direction of motion. Once I arrive there, well, I can use this simple recipe. And the recipe is the following. My radiative degrees of freedom in the TT gauge, of course you can work in different gauge, Ij will not be all of, okay, the time and time-space component, I just get rid by hand. I don't even talk about it anymore. And this space-space component, there would be 6 in general, no? Because this is a symmetric tensor 3 by 3, it would be 6. How do I go to 2? I apply a projector, which is done like this. I take the projector of a vector. This is a projector that takes a longitudinal vector to 0 and take a transverse vector to itself. And then my lambda is done like this. Pik pjl minus 1/2 Pij pkl. Okay, it's a trivial exercise, and I urge you to do it, that if you apply, this is a projector first, the square of it is itself, and its eigenvalues are only 0 and 1. And then if you apply to a generic symmetric 2-rank tensor, it spits you back the TT part, okay? So this is just a recipe, okay? This is just a recipe that is very, very handy to do computation. Instead of, finding a gauge transformation that kills some of the components, no, forget it. Once you understand that the theory is true, you just apply this. It's just a simple machinery. You apply this to the 3x3 matrix, and you get the TT part. Of course, you have to understand that it works, and the understanding that it works, it came from what I discussed in the previous 20 minutes. So at the end of the day, this derivation that I did, I will never mention it again unless you ask me to, and I will only use this. I will use the lambda projector, and that's it. Okay, I hope are you happy with that? So I could have done also in the electromagnetic case, no? I apply this to the original A field, and that's it. The only doubt you might have, well, look, but this is local in direct space. Whereas I learned from the gauge field that the composition was non-local in direct space. Yes, but here I'm using a wave propagating a specific direction. So it's like going to Fourier space, no? If I choose a wave going into a specific direction, it's like having one specific K. So it's a very specific case of direct space. It's the direct space which is the Fourier transform of a specific component of the Fourier space. So I can apply this projection happens to be local in direct space because here I project for a specific direction of propagation. This, of course, if I change the direction of propagation, this projector change. Okay. So in particular, no? Okay, we'll see application of this extensively. But just to, I mean, the idea is that to arrive here so that you can digest this, and once you accept it, you just use it all the time. But I think I demonstrated that this is correct. And then you can go over the demonstration and see if you can really accept it or not. So, how much time do who is?
Maybe some
Yes.
10 more minutes. 10 more minutes, is that okay?
10 more minutes plus question, or 10 more minutes including questions?
Including questions in principle.
Okay, then I stop for questions now. If you don't have question, I go on, so it's more for you. Okay, you don't ask, I go on. Shall I? I cancel everything. By the way, this sounds, I mean, if you've never seen this might sound curious, but it's exactly the same that you are doing in electromagnetism under the hood. In electromagnetism, it goes exactly the same, so you have one index less. So you don't take out the trace, say. But the transversality thing is the same thing. You just apply the transversality thing now to both indices, and then in addition, you have to take out the trace. And by the way, there is a nice theorem in field theory that all the relative degrees of freedom of spin 1 and spin 2 field, there can only be 2. This has to do with the little group of massless particles.
Sorry, may I ask a question real quick? Don't know if here.
Yes.
Don't know if that makes that much sense, but like, how would these constructions change if we introduce the cosmological term, so lambda non equal to 0? I mean, could you still be able to do these gauge transformations and all that? How would it affect?
But in particular, if you expand over Freeman-Robertson-Walker background, the question was about what does it change. You had the microphone, so I don't need to repeat. What happens is that the box is not the box of Minkowski, but is the box of Freeman-Robertson-Walker. It just happens. I mean, you can work it out. You compute the G mu. Instead of computing over Minkowski, you compute over Freeman-Robertson-Walker, and what comes out at the linearized order is basically this.
But you're going to solve pretty much the same equation. You solve pretty much the same equation at the end of the day.
Yes, you solve pretty much the same equation. And yes.
All right, thanks.
We'll see on Friday if we have time the gravitational equation in an expanding background, because they have to do with the cosmological application of gravitational wave. But I guess nobody's doing cosmology here, right? Apart from my students, of course. They have to know everything about gravitational waves. Otherwise, I beat them. No, I'm joking. Okay, so what do we do now? Yes, the multiple expansion, yes. So let's, now that we have that nice solution, let's apply it. So there was minus 16 pi g, there was minus 1 over 4 pi from the green function, so I get 4g t kl lambda ij. So writing the lambda is very boring. Sometimes I will forget it. So, and then I will put a tt on the source. That means the lambda projected. T minus x prime, x prime. Yes. Okay. This will only take 5 minutes to do this, so it's a good time. So unless you have other question, I will go on 5 minutes with this, and then I stop. Are you sure I go on 5 minutes? Yes, I do. Okay. So this is the solution. I just plug in the green function, the retarded green function. I haven't given you the relationship between retarded advance and Feynman green function. So they're all in the exercises. Today in the afternoon I won't be here, but if you're curious to know the relationship between Feynman advance and retarded, you find nicely written exercises, written by me, by the way. And so try to do them, and then if you have any problem, we can discuss. I mean, I'll be here all the time, just today in the afternoon I won't be here. So we can discuss anytime. But this is the retarded green function in the direct space, which, okay. So look at this. Okay, this is formally is correct, but yeah, it's not very manageable. No? I mean, what do we do with that? What do we do? You see here there is the retarded time. It means that when we're looking here, this is our detector on Earth, which is an eye, but let's put an interferometer. This is the gravitational wave arriving from very, 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 very far away. And you know the source is very small. It's hundreds of kilometer size. So this distance is huge, it's megaparsec, no? So, okay, look, here for instance, this depends on t and x. This x is the distance, and this x prime instead runs only over the source. So let's forget about this and just write d, the distance. This distance is really, really, really huge. Whereas x prime is moving over the source. So then even here we cannot really forget about x prime. Why? Because we have to consider what the source sends us in correct phase. No, this point of the source, we see it slightly later time than this point of the source, which is farther away. And since the time variation of the source is not too different than the size of the source, you remember the time variation, the period is basically 2 pi r over v, where t is related to the time variation of the source, and r, the small r, is related to the size of the source. So they are different, but not too different. There's not 10 order of 20 order of magnitude difference. It's just 1 over v difference, okay? So I had to take into account that this point is seen a slightly different time than that, okay? How do I do that? Well, I expand x minus x prime. I use the generalization of the Pythagoras theorem. This is the square root of x squared plus x prime squared minus 2x x prime. So, and this is basically the distance, 1 minus my direction. Yes. Okay. More or less. I have to keep this first order. Why? Because look at this here, what happened. Here I get 1 over d that goes out. And then I get t, k, l, t minus r, sorry, minus d, plus d and d simplify, basically n times x prime. Okay? Here I rightfully forgot. Here there are higher order, no? That go as x prime squared divided by d squared. This I completely neglect. But this first order in x prime over d, I keep it. Why? Because you see, the zero order combines to t minus d to give the retarded time. And this, whatever it is, I have to keep it. So my source at the time t, my field at the time t, depends on the source at the retarded time plus some little modulation. And this little modulation, this now I can expand in Taylor. So this will give me 1 over d, tkl of retarded time full stop. This is the zero order, plus t dot. Okay, here I forgot the dependence on x prime, okay? I just lazy to write it. Then it will be t dot times add dot x prime plus t double dot over 2 n dot x prime square, okay? So this is a Taylor expansion. Whenever I do a Taylor expansion, you have to remember, you have to check that I'm expanding a really small parameter, no? Otherwise, it doesn't make sense. So what is the small parameter that allows me to go from here to there? So first, let's check the dimension. This is the direction of propagation, is dimensionless. This is x prime, is the size. But here I have a time derivative, so dimensions are fine. Okay? So look at this. Here I have energy momentum tensor. Here I have energy momentum tensor, all computed at the same global time. Now I have only one time for all of the points of the source, the retarded time. But then I have this little modulation. So when I take the t dot, it's like divided by the typical period of the source. And when I multiply by x f prime, is I multiplying by the size of the source. Size of the source divided by typical period of the source is velocity, internal velocity of the source. So this expansion, it's an expansion in velocities, of internal velocity of the source. So this is more than that with the power of v, this is more than that with the power of v, and so on. So this expansion makes sense as long as the source is a small internal velocity, or not too close to 1. So now the next step is to trade this integral of TKL, integral of TKL x m, and m, integral of nm and n, integral of TKL xm xn. All of these are x primes. So I have to trade this for something more meaningful. I mean, this makes sense. I mean, lots of sense. But it's just that this is the space-space component of the energy momentum tensor. It's not something we're really used to. It would be better if it would be the integral of some 0,0 component of the energy momentum tensor. But this is, it cannot be, no? Because this has 2 indices, this has 0 indices. So it cannot be. I mean, 0 space indices. And moreover, this, what is the typical scaling of this object? This must be the kinetic energy, no? M, Vk, Vl, no? This TKL. Whereas this is just the total mass. So a raw guess that what we want to trade this for might be, okay, why don't we trade with the second moment? This has 2 indices, this has 2 indices. And, but this is not the right dimension because this is energy density, this is energy density times a distance square. Well, let's put 2 derivatives. If we put 2 derivatives, now Lorentz indices are okay. Scaling is okay because this is mass L divided by T, L divided by T, this is mv square, this is mv square. So yes, we can opt to trade the integral of the space-space component of the energy momentum tensor for second moment of suitably derived second moment of the energy momentum tensor. And here the same. You can hope to trade this for third derivative of third moment, and so on. And so tomorrow we'll see this. We'll see how to trade the integral of the energy momentum tensor for second moment, third moment, and so on. And this will be the last thing that we'll be doing at the level of the equation of motion. And then we go back to the Lagrangian, and then we treat the Lagrangian of the radiation. And then we go back to the scale of the source. How to model these moments of the source in terms of the dynamics of the binary system. So we'll have a theory here for the very short scale at the, inside the binary, and then we have a theory for the coupling of the gravitational wave to the suitable moments of the energy momentum tensor. Of course, these 2 theories, they are not independent because they both come from, everything is general relativity. It just, for phenomenological purposes, theory is split into a near zone theory of the internal dynamics of the source and to a far zone dynamics where the gravitational radiation couples to the moments of the composite source. Okay? From far away, this would be a composite source, and that will have some moments. And then the non-trivial point will be to match the moments of the composite source into binary dynamics of my specific system. This is basically what we'll be doing from now to Friday. But, yes. Okay, I stopped here basically today. I didn't do these last 2 points. But okay, I will do tomorrow. Okay, stop.
Okay, so unfortunately, I don't think we have time for questions. You missed your opportunity. But
yeah. So since I'm running a bit late, So the green functions, I move to the exercises. So tomorrow I will not do this, but tomorrow, I mean, you can already do the exercises, which are in the notes. And if you have any problem, we can talk tomorrow afternoon in the exercise session. No, the energy of gravitational waves, I have to do it, otherwise I cannot go on. So next time, tomorrow I start from the energy of gravitational waves, and we move the green function discussion to the exercise.
Okay, so let's have lunch and be back here at 2 o'clock.